conservation laws for physical systems and symmetries described by continuous groups. This is said to be a very, very important concept and set of results in the physics of the last century. And I would guess that, I'll tell you a little bit of history. I would guess that its greatest impact has been in the fields of atomic physics, nuclear physics, elementary particle physics, basic quantum mechanics. Those are the areas in which these results have had maximum impact. Now, this fact that this is on YouTube, is it correct?
Yeah.
Today also?
Yeah.
It acts like a constraint. I feel hesitant to say some things because somebody somewhere in the world may say, why is he saying all this? But my audience is right here.
That's right.
You are correct? Is that right? Okay. 12. Okay. Yeah. The great result in this field was obtained in the year 1918 by a woman mathematician by name Amy Amalie Noether, Noether. So, this result is called Noethers Theorem. A little bit about Noether. This is a kind of thing I hesitate because it's on YouTube, but okay. She's often been called the greatest woman mathematician of all time. Certainly of the modern era, there is no question about it. Even people like Hermann Weyl and Albert Einstein expressed this opinion that she was supremely gifted mathematician. And the amazing thing is her mathematical strengths were in the area of what is called abstract algebra. And I have heard mathematician friends in TIFR tell me that it is her work that gave rise to modern algebra as a major part of modern mathematics. There are phrases like Noetherian rings and theorems by her in that field and so on. So, she seems to have been a very, very original thinker. Unfortunately, in that period, the early part of the last century, in most of the Western world, women were not treated well in academic life. There was another person, Lise Meitner, a very talented experimental nuclear physicist who just could not get any faculty position anywhere for many, many years. Finally, she got a position in Sweden, in the University of Stockholm. So, as for Noether, just tidbits I just want to tell you. Who was her PhD guide? Formerly, she was one of the students working around David Hilbert. Now, people who study quantum mechanics and especially quantum theory of angular momentum must have heard this pair of names, Klebsch and Gordon. You have all heard of them? So, by the way, Klebsch was the one who wrote down the lecture notes of Jacobi's lectures on mechanics. And I told you that has then been translated into English by Bala Gangadharan and it is published by Hindustan Book Agency. So, Klebsch is known from that context that he wrote down Jacobi's lecture notes. So, Gordon, I think Paul Gordon, Gordan, was a very senior mathematician in the group of mathematicians led by, you can say, David Hilbert. And Gordon was approximately 60 years old, I believe, when he agreed to become Amy Noether's PhD guide. And then she did her degree. After that, she had a lot of difficulty finding a place where she could, faculty position. It was very difficult. And she would not even be allowed to teach at the university in Göttingen because those were the rules at that time. And there is some famous remark that Hilbert made. Well, you should read it. There is a beautiful biography of Hilbert published around 1965 or 67 by Constance Reed. And the name of the book is just Hilbert. She was not a mathematician, this writer, but she has written this book in such a wonderful way, conveying the mathematical ideas of Hilbert, though she was not a mathematician at all. And so in that book you will find a picture with the Klebsch and Gordon sitting next to each other and Hilbert on the other side of the table. You will get a feeling for the people there at that time. And she also talks a little bit about Noether. Finally, I think those who wanted to help her managed to get a position for her in a well-known college in the USA near Philadelphia called Bryn Mawr. I think this is a Welsh name, and maybe there was a group of people from Wales who had emigrated to the USA and they had set up this college. And so she worked there. Sometime in the, I don't know, late 30s or something like that, she finally went from Europe to the USA and was at this college. Unfortunately, sometime in the mid-1940s, she died because of a very sudden health problem, something like appendicitis or something like that. She just passed away. Okay, so this is about Noether. And I am always impressed. I don't understand her work, but I'm impressed by the fact that she had a capacity to think in such an abstract way, no mental pictures of any kind. Where her motivations came from, God only knows. How she had that gift. And if I may mention it, there's one person who was in the TIFR School of Mathematics who had that kind of gift, Professor Raman Parimala, right? So I don't know where they get this kind of intuition. You might have also noticed it. No?
Actually, I knew Parimala very well as a colleague.
Yeah.
I didn't know her mathematics, so I cannot.
But I also don't know her mathematics, but the style in which whatever she did was very, very abstract. And you would wonder where did the ideas come from, not in anything they saw around themselves in the world. No? So it's very interesting. So I just thought this is important to know. Okay. So in 1918, just a few years before that, this general theory of relativity had been constructed or discovered by Einstein, and there is a feature of general relativity theory which says, that in special relativity the idea of inertial frames, which I talked about on Monday, is still there. It is a very important part of special relativity. And when you make a transition from one inertial frame to another inertial frame, the space-time coordinates change according to the Lorentz transformation equations. But when Einstein went next to the general theory of relativity, the transformations that he said are permitted on the space-time coordinates are not Lorentz transformations, but any transformations at all. You can start with x, y, z, t, replace them by x prime, y prime, z prime, t prime, new space-time coordinates, functions of the old. Each one can be any function of x, y, z, t, provided it has an inverse. And he said that his guiding principle was that the equations of general relativity should preserve their form under such transformations, arbitrary changes of space-time coordinates. no notion of inertial frame in a global sense, etc., etc. And I think I mentioned sometime David Hilbert was following what Einstein was doing. I mean, Einstein worked from roughly 1907 onwards to construct general theory of relativity. It went through many stages. He got partial results. 1911, 12, he had some results. Then he thought he had solved a problem, and he found he had made major mistake. He backtracked, etc. Hilbert was following what Einstein was doing. And at the end of the story, while Einstein was struggling to obtain what are called the field equations of general relativity, I believe by a few days, 1 week, 5 days, Hilbert got them before Einstein. What did he do? He guessed a Lagrangian for the general relativity, and he did a Hamilton's principle, and he got the equations. But the point is that all the physical insight which went into the construction of general theory of relativity were in Einstein's work, not in Hilbert's. At that time, Hilbert asked Noether this question: what is the status of conserved quantities, integrals of motion, in a theory like general relativity, where you are allowed to make arbitrary changes in coordinates, space-time coordinates? What qualitatively new things come? And it was this problem that Noether solved in a very famous paper in 1918. And ever since then, it is regarded as one of the key results for modern physics, classical level, which is what I will describe, also at the quantum level. So, in today and tomorrow's lecture, I want to bring out this close connection between continuous symmetries of classical systems and constants of motion. This is what I want to describe to you. This paper of Noether, I had not read it myself. In every book on quantum field theory written over the last 40-50 years, every one of them, somewhere in the first chapter or second chapter, there is a section on Noethers theorem. After that, people forget about it in the rest of the book. Okay? But it turned out that in most books, what the authors call Noethers theorem, this connection between symmetry and integrals of motion, is a very small part of what she achieved in her paper. And that is what I want to emphasize here. Even I, for all these years, was not fully familiar what is the extent of what she had done. Then about 2 years ago, 2016, the TIFR's ICTS in Bengaluru arranged a 2-day meeting in honor of Noether to review her work, mostly on mathematics. And they asked Joseph Samuel of Raman Institute and me to talk about this Noether theorem. At that time, Samuel managed to get on the internet a good quality English translation of Noether's work. That is how I got to read it for the first time in detail. And I realized how much she had done, going beyond what is normally described as Noether's theorem in most books on quantum field theory. This is what I want to tell you. So, because her aim was to answer Hilbert's question, how does the fact that you are demanding some equations which preserve their form under arbitrary changes of the independent variables, how does that affect the existence of definition of energy, definition of how can we define such things, and so on. Okay. So, it was a chastening experience. She had done much more than what most field theory books in physics tell you she had done. But then I found out that she had gone up to a certain point And as far as I can, and you know, this, her writing, the mathematical background, the writing is very dense. It's very hard to understand exactly what is meant by each sentence. So I have a project to go back and read it again. It is some 18, 20, 25 pages long in print. Yeah, it is fairly long. But I did find one thing. She took the her work was entirely in the classical domain, classical field theory, you can say. There was no quantum mechanics yet in 1918. So she got her results assuming the framework of classical field theory, classical Lagrangian field theory, I should say, classical Hamilton's principle in that framework. But she did not carry, this I can say with conviction, she did not carry the discussion to the level of the use of phase space. That is what I found from her work. At least I have to reread and make sure I am not missing something hidden in some small phrase somewhere. As far as I know, that part she did not pay attention to. So that is the thing that I want to cover, that gap. Okay. Now this, what I am going to describe now has been written in an article in Resonance by some of us a few years ago. So I will, this is freely downloadable, Resonance volume 16, page 129 to 151, 2011. Okay, almost 8 years ago. So now I will do the following. I will go through this description of Noethers theorem in a step-by-step manner, start with very simple situations and then go on to the more sophisticated versions of it. So for the equations of motion, we have seen that we can deal with them in 3 stages. We begin always with the Newtonian equations of motion. Then we have seen how to rewrite them in the Lagrangian form, and finally in the Hamiltonian form. And each of these steps from a mathematical point of view is increasingly more sophisticated, though the physical content is always the same. This I would like to stress. So now I will give a parallel treatment of the connection between symmetry and conservation laws. To begin with, in the simplest Newtonian language, then we will transfer it to the Lagrangian language, and finally to the Hamiltonian language. And as far as I can make out from Noether's paper, this part she has not dealt with in her paper. Okay, the last part, as far as I can make out. Yeah. And you introduced a distinction between conserved quantities which have no explicit time dependence. You call them integrals of motion. And if there is a dependence on time explicitly, you call it a constant of motion. So I will just use this one name, constant of motion, and in general I will allow explicit time dependence, but maybe sometimes it is not there. All right. So the first case I will remind you. So I start with very simple situation described by Newton's equations of motion, and imagine a system of 2 bodies with masses m1 and m2. Then what is the structure of the Newtonian equations of motion? First of all, and here of course I am using Cartesian description, Cartesian coordinates. I have the three Cartesian momentum vectors P1 and P2 given in terms of the velocities in this way. And then the equations of motion are equations which tell you how the momenta change, rate of change of momentum. So, let us say capital F is the force on body 1 on M1 due to M2, wherever it may come from. Then this is the content of Newton's third law of motion, that if you have a force F in the equation of motion for the first particle, the force in the second one is minus F. To every action there is an equal and opposite reaction. In a light-hearted way, my good friend V. Balakrishnan, you have heard this, he says that in his state, when he asks incoming students in the interview, can you state Newton's third law of motion? They said, yes sir, to every action there is an equal and opposite revenge. So this is when the language is a little unfamiliar, this can happen. So this is the expression of Newton's third law, that the two forces are equal and opposite, and you can see from here there is a constant of motion, the total momentum. I had mentioned in the first lecture that Newton's third law was his own independent contribution to the foundations of mechanics, and that it is connected with conservation of momentum. So this was the first conservation law in the history of mechanics. At this stage, you don't see any connection between the existence of this conserved quantity and any symmetry of any kind. Now I go to the next step, and there you will see the importance, the relation, connection to symmetry. Suppose that the forces F and minus F arise from a potential, an interparticle potential. Then the force on M1 will be the negative gradient of a potential, gradient with respect to coordinates of a particle 1, of a potential which depends only on the separation between the two particles. And for I'm mixing up 1 and 2 subscript. So the fact that the potential depends only on the difference between the two coordinates, coordinate vectors, ensures Newton's third law. Everybody knows this. But now we can express it in another way. We can say the existence of the total momentum as a constant of motion is related to translation invariance. If you shift both position vectors x1 and x2 by a common amount, x1 goes to x1 plus a, x2 goes to x2 plus a, the potential is unchanged. So in this way, the conservation of momentum gets related to a symmetry. Okay, all right. So next case is to bring in the Lagrangian system of equations of motion. In general, in the Lagrangian description, the complete set of equations of motion given a Lagrangian is this. for all the degrees of freedom. These are the Lagrangian equations. Now, we say that we have a constant of motion if the following is true. If these equations of motion imply that the total time derivative of this quantity f, some function of all the generalized coordinates and velocities, is 0 as a consequence of the given equations of motion. Then we say f is a constant of motion. Then, as you can see very easily, along any solution of the equations of motion, this quantity f, physical quantity, has a constant numerical value, namely its value at an initial time. Now, of course, you can easily extend it to the case where this f has an explicit time dependence. I don't have to worry about it. Now, in this statement, this is a very simple-minded statement, and usually you may not find this written in books at this level. Usually, after the Hamiltonian equations of motion have been derived, then a constant of motion is shown to be something whose Poisson bracket with the Hamiltonian is 0. But I want to bring it in at the Lagrangian level. All these ideas are quite elementary. Now, in this statement, the definition of a constant of motion in Lagrangian mechanics, once again, there is no obvious link to any kind of symmetry. But now I move towards that kind of connection. Somebody asked, yes, a few days ago about cyclic variables, and this was also discussed in Shamik's lectures. Suppose L, the Lagrangian, has no dependence on one of the generalized coordinates. Let us say it has no dependence on the kth generalized coordinate for some k, but of course it does depend on the corresponding generalized velocity. Otherwise, if neither q nor q dot are there, it's not there at all. So, then you can see from here, from the equations of motion, take r equal to k, this term is 0, dl by dqk is 0, no dependence on qk, and therefore that equation of motion reduces to a simple statement. This implies the corresponding momentum is conserved. And this is what is called the case of cyclic coordinates. And this is what was used in the action angle variable method, where the thetas are all cyclic variables and the momenta p's are the action variables I. So, it may be that there are several cyclic coordinates. For each one, the corresponding canonical momentum is conserved. Can we express this in the language of a symmetry, invariance under a symmetry transformation? Yes, it's very trivial. We are saying here that this Lagrangian has no dependence on the generalized coordinate qk for some k. So, what it means is the following. Imagine that you shift the kth coordinate alone by a small amount, epsilon is a small amount, the other q1, q not the kth, you don't shift. Then obviously under this kind of small change in the generalized coordinates, we are saying the Lagrangian is unchanged. It's a trivial statement, but I want to show it as a consequence of the Lagrangian being unchanged by a certain given transformation of the generalized coordinates. That is this. So, here in words we say, suppose qk is absent in the Lagrangian for some k. I am writing it in this way. Under a translation of the kth generalized coordinate, let us suppose the Lagrangian is conserved, it is invariant. Then the corresponding p is immediately seen to be a constant of motion. So, this is the case of cyclic variables. Now, just a side comment so that you appreciate a slightly delicate point. As I have said often, the Lagrangian formalism always allows for explicit time dependence in the Lagrangian, in the transformations you consider, and so on. Suppose the Lagrangian has no explicit time dependence. Suppose, okay? In that case, loosely speaking, you might say, that is, suppose there is no explicit t appearing in the Lagrangian, then we might describe it by saying, in this language, time is cyclic. But it has to be understood in a proper way. Here we say we have a cyclic situation coordinate if that coordinate is absent in the Lagrangian. So, now if I have a Lagrangian which has no explicit time dependence, shall I say this is a case where time is cyclic? You can make that statement, but you should not misunderstand it. Time is not a generalized coordinate, but the absence of explicit time dependence can be expressed in this way. So, it does turn out that we do have a corresponding constant of motion. From this condition, you can extract a constant of motion. It is not so trivial as the previous statement, because the Euler-Lagrange equation for degree of freedom k immediately told you d by dt of pk is 0. But now you have to do just a little bit of work, because this means that the total derivative of the Lagrangian, taking into account time dependence of q dot inside, will be made up of two terms. Right? Partial derivative with respect to every coordinate times the corresponding velocity. Partial derivative with respect to every velocity times the corresponding acceleration. This is total time derivative. Now, if you use the equations of motion, then this part can be rewritten. So, this becomes when the equations of motion are satisfied, this expression can be rewritten in this way. I have used the Lagrange equations of motion to write d by dq of the Lagrangian in this way. Now, what is this? Isn't it a total time derivative? What is this the time derivative of? I hope all the dots are easily visible. These are two dots here. What should I put inside the bracket? Huh? Yeah? Very good, very good. Correct? So, you can see that when the equations of motion are obeyed, if the Lagrangian has no time dependence explicitly, you get this consequence. Now, look at the left, this is a total time derivative, right is a total time derivative. So, what is the conclusion? Bring both terms to one side, and then you find that this Legendre transform of the Lagrangian is a constant of motion, an integral of motion, because there is no explicit time dependence. So this is a very elementary thing, and I just wanted to show you that it is a simple consequence of the idea that even though time is not a generalized coordinate, it is the independent variable, we can use this language provided it causes no misunderstanding, and we can say, like the case of actual cyclic variables, in which case you have corresponding conserved momenta, here also you have a conserved quantity. Many years ago, 1972, I was telling Professor Burma, we all together in TIFR conducted a all India advanced summer school on quantum mechanics at the request of UGC. And there I found that in different parts of India, people use different words for partial differentiation. I found there was an audience from all over the country, and one person would say d by dx, d by dy, d by dz. Another would say delta by delta x, delta by delta y, delta by delta z. Third person, dou by dou x, dou by dou y, dou by dou z. Fourth one, you know what it is? Huh? Daba by daba x, daba by daba y. Isn't that right? Now I forgotten which part of the country uses what. I remember.
What is used in Bengaluru?
Huh? I don't know. All are correct. Locally correct. Yeah, very good. Global. Yeah. Okay. So for all non-relativistic systems where the Lagrangian has a quadratic kinetic energy, quadratic in q dot, and then there is a minus a potential, this is indeed the total energy. Okay, so the cases I have described up to now are extremely elementary. Now we will go towards little more sophistication in the spirit of Noether's work. So we are in this part of the board. Now, when we derived the equations of motion from Hamilton's principle, we had a version, the more sophisticated version, where we imagine variations which are not vanishing at the end points. Okay? So, I will remind you of the expression we saw for the change produced in the action functional in this kind of situation. There is the main term, body of the expression, which is this one. And then we saw that if we have variations which do not vanish at the end points, I will use this notation. Well, I should really call it E in that way. So, okay, I'll be careful. This is the expression for the change in the action under a variation which is not required to vanish at time t1 and t2. You are allowing the initial and final times to get shifted a little bit. You are allowing the initial and final configuration also to get shifted at the end points. Now you can see that, and this is true, this expression, this result is true for any choice of small changes in every generalized coordinate at every time from T1 to T2. You can choose delta q as you like, completely unrestricted. That is, this is true for arbitrary choices of small changes in coordinates all along the motion. Now I use this in the following way. Just a minute. Suppose the equations of motion are obeyed. Then this term drops. Then I say, I am not interested now in arbitrary choices of the variation delta q. I imagine that the change in each generalized coordinate at each time, I imagine, is some small parameter epsilon, because these are all small changes, times a specific given function of the q's. So, delta q1 shall be this common small factor epsilon, numerical factor, times a function phi 1 of q. Delta q2 shall be same epsilon, some phi 2 of q, and so on. Now, here is a very simple example. Supposing you took Cartesian coordinates for a particle in 3 dimensions. Then the changes in the Cartesian coordinates x, y, z of a particle under a small rotation, infinitesimal rotation, what do they look like? Well, if the angle of rotation is a small angle, that epsilon is here, and then the rotation is in the direction of an axis n in 3-dimensional space. Do you all know that this is the way in which every Cartesian coordinate of a particle changes under a small rotation? Are you familiar with this? Epsilon is a Levi-Civita symbol. So, the parameter epsilon is the magnitude of the rotation, small angle. This nk is supposed to be a unit vector, is the axis of rotation, and this is the way in which delta x comes out. In spirit, it is very much like this. We are imagining now changes in every generalized coordinate, all proportional to one common small factor, infinitesimal changes, and then multiplied by some given function of the coordinates. So, we are imagining that there is a transformation of this kind, and we will suppose that under this, let us imagine that the Lagrangian does not change. So, I have a Lagrangian L of q dot. I imagine replacing q by q plus delta q, some expression of that kind, and q dot by q dot plus delta q dot, where by definition delta q dot is to be thought of as the time derivative of delta q. So, these are all small changes, infinitesimal changes. Suppose that the Lagrangian is unchanged by this transformation. Then we will say we have a point transformation, because the changes in q are dependent only on q in this example. We have a point transformation which is a symmetry of my Lagrangian. If it is true that after changing q in this way, q dot in that way, there is no change in the Lagrangian. So, such a transformation, point transformation, will be called a continuous symmetry of the Lagrangian if this equation is true. So, what does this mean? This means the change in the Lagrangian delta L caused by first order changes of this kind for given phi's is a continuous symmetry of the Lagrangian. Now we can immediately produce the equation of the constant of motion. What I will do is I will just actually I may not take the full 90 minutes today because like these batteries I am running out a little bit. So I will go as far as I can, and then we can have some amount of discussion. So what does this mean that the change in the Lagrangian is 0? Well, the change in the Lagrangian is made up of two parts. A piece coming from the variations in Q and a piece coming from the variations in Q dot. All right. And we know what delta Q is and delta Q dot is. So what I will do is I will pull out the common small factor epsilon, which is just to keep track that it's an infinitesimal transformation. So do you see that this is what I have? Epsilon is a common small factor denoting the fact that it's an infinitesimal transformation. The first term comes the contribution to the change in the Lagrangian because of the small changes made wherever the Q appears in the Lagrangian. The second term is the contribution from the small changes in every velocity delta Q dot. So these are the two terms. All right. Now I will say, using the Lagrange equations of motion, this is, I say it is, apart from the factor epsilon, d by dt of an expression canonical momentum for each degree of freedom times the amount by which that coordinate changes under the transformation. Now I want to repeat, I am discussing here what is called a point transformation. A transformation defined on configuration space, taking any point in capital Q, moving it to a nearby point, depending only on Q. So it's a special kind of symmetry. If the Lagrangian you are interested in preserves its form under this transformation, we say it is a symmetry of this Lagrangian. And then you can see, as a consequence, when the equations of motion are obeyed, there is an expression whose time derivative, total time derivative, is 0. So you have a constant of motion. What is the constant of motion? I will use a symbol. Well, no, I'll bring G later. I just want to say there is an expression which is conserved in time, which is because the Lagrangian had a symmetry. The symmetry was the statement that under this point transformation, Lagrangian does not change. This is exactly the content, as physicists normally say, content of Noethers theorem. Of course, Noether, as I told you, used throughout her paper the formalism and the language of classical field theory, not of particle mechanics, but it can be rewritten in this language. You can easily do it for classical field theory, her notation. Now, so most books in physics, unfortunately, give the impression that this is Noether's theorem, but actually she has done much more. That has apparently not been properly acknowledged by most physicists. And I learned from Samuel, who also talked at this ICTS 2-day meeting on Noether, sometime in the 1950s, 57 or something like that, there was an article by some Hill in the Reviews of Modern Physics, describing for a physics audience the content of Noethers theorem. According to what he said at that time, that review article gave the impression that this is all that Noether had done. And then the physics community did not ever go back and read Noether's original work. They all took Hill's statement at face value. And all the textbooks on quantum field theory, the first chapter is on classical field theory. The section, one of the important sections is Noether's theorem. They just say this and leave it at that. So this is a misconception that has to be corrected.
Are there
Yeah.
constructions of phi?
Yeah. So supposing you have a Cartesian description of a particle in a spherically symmetric potential. All right. Then this is exactly the kind of effect of a rotation. This part is in this notation phi. Every Cartesian coordinate, the change is this common amount of rotation epsilon times. So delta x1 is proportional to the function phi 1 of x here. Delta x2 is phi 2, etc. And if the Lagrangian is spherically symmetric, that is, if it's half m x dot squared vector and minus a potential which is function of radial variable only, it's an example. So what I want you to appreciate is the following. The fact that there is this constant of motion can be immediately read off from this version of the action principle. This is what I want to emphasize. I will not go into the details. I will leave it as a small exercise for you to think through it. If the Lagrangian has this symmetry, in this calculation of the change in the action functional, we said we can allow the changes delta q and delta t to be arbitrary changes. Let us limit ourselves to a particular symmetry transformation, certainly allowed as a case of the arbitrary change. In that case, if the Lagrangian does not change, the action cannot change. The equations of motion are used, this part goes away. You do not have to invoke changes in the initial and final times. Imagine delta t1, delta t2 are 0. This is gone. Then what does the action principle tell you? When the equations of motion are obeyed, if the Lagrangian is symmetric under our delta q of this kind, this expression has the same value at the time t2 as at the time t1. It's obvious, right? So either you can do it in detail like this, or you can read it off from the action, so the expression for the action. So one can say the invariance of a Lagrangian under an infinitesimal point transformation. That means infinitesimal, everything proportional to small epsilon. Point transformation, every delta q is some expression involving all the q's. That's all. So if the Lagrangian is invariant under a point transformation, continuous point transformation, when you combine it with the Euler-Lagrange equations of motion, you have a constant of motion with a very specific structure. It is linear in the canonical momentum variables. That is the important thing. So symmetry under a point transformation leads to constants of motion linear in the momentum variables. Now this is true for translations. When you get for particle systems, total momentum is conserved. Well, total momentum is the sum of all the individual momenta. It is linear. Angular momentum coming from rotational invariance. It is the sum of all the orbital contributions, all the q cross p's, linear in p. The coefficient of p is a reminder of how much each corresponding q changed under the transformation. Okay. So this is and as I say in most physics books, there is a tendency to say this is all that Noether had done, but she had done much more. Okay. Now I go to the next step. Now all this had some, I'll use some notation. This discussion was, when you look at the notes, this is point F. Now I do the following. I want to take this result. So let me say again, I think you can easily, even on your mobile phones, trace this review article of Mr. Hill in Reviews of Modern Physics, roughly 1955, 56, 57, in that period. And just see what the title is and just confirm that what I have told you is correct. Right? Apparently, Buddha always told his disciples, don't believe everything I say because you have respect for me. You go and find out for yourself and decide, should you believe me or not believe me. So in that Buddha spirit, I am telling you, use your computers or mobile phones, get to see this Hill article, and it will give you a very good, it's a very nice, intellectually, very nice thing to see that if it is indeed true that Hill gave a very limited description of Noether's result, we must correct that impression in our minds and understand that she did much more. But now I come to the passage of this discussion to the phase space language. This part, I say, is not in Noether's work, as far as I can tell. For that you have to go and look at Noether's paper. I know that it is quite hard to follow. I told you, it is very dense. The mathematical style of those days, even today, mathematical style, very dense. You know? There is a famous book on Lie algebras by great mathematician from Yale University, written in the 50s or 60s. And it is written in such a way that nobody shall understand it. I am making a strong statement. Then there is a book on classical mechanics written in the 60s or so by Abraham and Marsden, expressing classical mechanics in the language of modern differential geometry. You try to read it. I don't know. Anyone with a physics background, you find it very hard to understand the motivations, why things are done in a particular way. Okay. All right. Now I want to show you something. I will write the constant of motion which we have found in this particular case, infinitesimal point transformation symmetry. I will write it as G of QP. This is the notation I will use later also. All right. That is, I am writing P delta Q as a small parameter epsilon times a function G on phase space. Now you can see, because the dependence on momentum is linear, what is the Poisson bracket of any one of the coordinates, generalized coordinates, with this constant of motion? What is it equal to? Huh? Sorry? No, that is Q with P. I want the Poisson bracket of any one of the generalized coordinates with this constant of motion, which has the feature, it is linear in the momentum. So what is the Poisson bracket of u with me? du by dq, d me by dp minus the other term, summed over all the degrees of freedom. only the first term will survive, because the second term, there is no momentum dependence here. So what is the first term in this Poisson bracket? D by dq of this times d by d corresponding p of that. So tell me, what is this? Use the definition if you wish, otherwise you should be able to immediately see it. Correct. It is exactly equal to right? Because G I have written as, sorry, there is no delta there. G is P times each phi. So you can put it in another way. Put in this factor epsilon, and then you see that the constant of motion, because it is linear in the momentum, its Poisson bracket with coordinate qs is the change in that coordinate under the symmetry transformation. And remember, this is a point transformation. We are still limiting ourselves to that. Now, you remember, I think yesterday I described the form of a general infinitesimal canonical transformation. I wrote it yesterday. This is the expression. Every infinitesimal canonical transformation is generated by a corresponding infinitesimal generator, some little g, delta little g. The change in every q is the Poisson bracket of that q with the generator. The change in every momentum is the Poisson bracket of that momentum with that same generator. So this we saw yesterday. This is the general structure of the infinitesimal canonical transformation. And where did we use it? We used it to interpret Hamilton's equations of motion, where you think of G as the Hamiltonian times delta t. All right. So now you can see that this is a trivial statement. The Poisson bracket of every q with this constant of motion with the parameter epsilon is the change in that q under the symmetry transformation. There is a simple calculation which you should do, and that is the following. Well, I should write it in this way. There is a natural way to define what we mean by the change in every momentum variable under the same transformation. I leave it as an intellectual exercise. You find out how you should define it. I don't want to go through the steps. When you define it in the physically reasonable manner, you will then find that the symmetry causes a change in every canonical momentum of this form. Poisson bracket of that momentum with the same epsilon times the constant of motion. So what does this show? For the simplest case of point transformations, which are continuous symmetries of a Lagrangian, there is a constant of motion. It has a very simple dependence on momentum variables, namely it is linear in them. The expressions for delta q already have the form that you expect from an infinitesimal canonical transformation. It is possible to define what we mean by delta p for this situation. Work out that definition, calculate it, you will find it takes up this form. And what I want you to appreciate is that it has turned out that any point transformation which is a continuous symmetry of the Lagrangian does several things for you. One, it gives rise to a constant of motion, G, capital G. Two, it tells you that the transformation when reinterpreted in the language of phase space, is a canonical transformation. Now, who told you this in the beginning? Nobody said so. This part of this is not there in Noether's work as far as I could make out. Now, I give it as a nice exercise to more adventurous of you. Maybe a couple of you can get together, trace Noether's paper on the internet, it's available, and then try to find out if there is anywhere there hidden a statement about what happens when you go to phase space. Of course, the notation is not of mechanics, not Q's and P's, it is fields on space-time, but you try to find out. So, then you find that every symmetry introduced in the language of Lagrangian mechanics leads to a constant of motion, and when the discussion is taken to the phase space level, two things pop out. The transformation on phase space is canonical. That was not at all put in the beginning of the discussion. And what else? The constant of motion is a generator of the symmetry. So, this is what I find extremely pleasing about this part, and this is what I want to emphasize. So, there are several things I would like to make, several statements. These are in the lecture notes which are accessible to you now, following equation 102. The statements I am making now are in my notes immediately after equation 102, and I will just read them out because they are available to you. Invariance of a Lagrangian under an infinitesimal point transformation leads to a constant of motion linear in momentum. So, that part is clear. Second, the action of the transformation on phase space can be defined in a natural way. Delta Q is already given to us. We can define delta P in a physically reasonable way, and then when you calculate delta P and attach it to the result for delta Q, overall it turns out to be an infinitesimal canonical transformation. So, I want to stress the idea that a symmetry should be a canonical transformation was not one of the starting assumptions, it is a consequence of the analysis of it. In the case of point transformations, it turns out the equations of motion are not needed to get this result. This is just a technical point I just make. The fact that delta Q is a bracket of Q with the constant of motion is trivial. Just look at it, it's linear in P. This calculation, it turns out, for a case of point transformations, it does not involve use of the equations of motion to get the structure of a canonical transformation. And last statement, which I have not gone into in any detail, I will not prove it, but it's a very nice thing for you to convince yourself using the action principle. That's the most economical way to do it. If you have any solution of the Lagrangian equations of motion and you have a symmetry of this kind, you apply the symmetry to that solution, what will the result be? It will be in general another solution, not the same solution, but another solution in general. So, it means that the set of all solutions of the equations of motion, symmetries of this kind can act on that set, and you take one solution, one trajectory in configuration or phase space, the symmetry will take you to another solution. In general, it is not true that symmetries of the equations of motion are symmetries of the solutions. That is the mantra, key mantra. Symmetry of equations of motion in general symmetries of a differential equation in the mathematical language only tell you if a differential equation is preserved under some transformation, one solution will lead to another solution. Property of being a solution is maintained, but not a particular solution. This is the very important thing. Okay. So, I want you to convince yourself, acting on any solution of the equations of motion, the symmetry transformation leads in general to another nearby solution. This is a general statement. Now, all of these statements are very important. Putting it in the language of phase space is very important in the quantum mechanical context. There what happens is that where we use canonical transformations, here we say every symmetry transformation is represented by a unitary operator on the wave functions of a quantum system. And if it comes from a symmetry, the generator of the unitary transformation is the constant of motion. Now, that seed of that result is already here. And I, at the risk of incriminating myself, I will repeat, as far as I know, this thing is not there. This idea is not there in the Noether paper. But I will be happy if any one of you is able to reach her paper on the internet, have a look and tell me later today or tomorrow, am I right or am I right? Yeah. So, there is a very nice triangular relationship for point transformations, and it is the following. We are talking of continuous symmetries of a Lagrangian system. So, I will not repeat that. The symmetry, as we have seen here in this case of point transformation, leads to a constant of motion g. When you bring in the phase space language, it turns out to be a canonical transformation. The action on coordinates was given to you, the action on momentum variables can be defined in a natural way and calculated, and then you put the two together, it's an infinitesimal canonical transformation. And then, lo and behold, this constant of motion, it has two roles, two faces, like Janus. It is a constant of motion, it is preserved along every solution of the equations of motion. It also, in the algebraic sense, not in terms of numerical values, produces the symmetry. It actually takes any solution of the Lagrangian equations and out of it produces another nearby solution. Preservation of the equations of motion means preservation of the property of obeying the equations of motion, not an individual solution. Okay? So, this is very important. And you know that in quantum mechanics, these things get very much more subtle. If you look at the problem of the orbits of an electron in the hydrogen atom classically, you know that they are plane, they are ellipses and so on. The Coulomb problem or the Kepler problem is rotationally symmetric. So, the corresponding constant of motion is the orbital angular momentum. The orbital angular momentum generates the rotation. So, it is like saying the constant of motion, in gratitude to the symmetry which gave rise to it, says, now I will show how you have to act. Now, I like to picture it in that way, make these things a little more humanoid or whatever it is. So, this triangle of relationships is very, very important. And now in quantum mechanics, what happens? In the classical Kepler problem, every solution of the Newtonian equations of motion will be a elliptical orbit in some two-dimensional plane. And you make any rotation, most of the time it will tilt the plane of the orbit, you will get another orbit in another plane after you apply a rotation. What happens in the ground state of the hydrogen atom? Because there are no orbits, there are only wave functions. In the ground state, the wave function itself is spherically symmetric, which is completely quantum mechanical property of the motion. It is not there at all at the classical level. So we have to appreciate that. Okay? Okay. I will stop here. I have run out of energy. So few minutes for any questions, comments, surely.